Assalamu alaikum, bismillahirrahmanirrahim. Bishali Sadri Wasamri Wahlul Misani Fogari. Just like in the workshop we have conducted in Mechanical AV Hall and in the University, I just like to share a short video of tutorial regarding the Excel chart for calculating the diameter of a pipe for simple piping flow for underground tank to overhead tank, or for utilizing water from overhead tank to underground and for any domestic need. So just like in the presentation, I shown these pictures showing that in designing or constructing any building, you have a team of engineers for whether you are in a client side for monitoring its quality or monitoring overall operation for cost effective project, or either you are in the consultant firm who actually designed this building, not only the architectural plan but also the civil. And after that architectural and civil, you have part of the companies working for its HVAC MEP. What does HVAC MEP stand for? Heating, ventilation, and air conditioning system. That is showing in this picture. For central air conditioning, you have a central chiller, and from this central chiller, the air is transferring from different section of the building, different floors and offices of the buildings. So some ducts are returning air, that the air is coming returning from the rooms to the central chiller, and then it is conditioned by the temperature and the humidity and sent back towards that particular room, so on. So you have a HVAC system, and another one system which our engineers are working on are mechanical, electrical, and plumbing. That is related to the water transferring from overhead tank or underground tank to overhead tanks for any domestic need. And in the industries, we have the piping system not only for the water but also for processed water, for sewage water, rain water, for especially in the steams, for a lot of process we have utilizing compressed air and steam. So you have these kind of complex drawings, whether it is in the 2D form, and the 2D form it is said to be plant and instrumentation, piping and instrumentation drawings. Just like this, you have plan over like this. This is an actual aerial view of a storage facility. We have a storage facility of uh, heavy furnace oil, HFO, and the diesel tank. And for the safety, we have a fire hydrant system which transferring water to the fire hoses nozzles. In case of fire, we have to the pump will run and the water is transferred to this tank to prevent this further fire. Okay, so you have a system like this after architectural and civil plan. So today our video is related to the tutorial regarding the pipe diameter of simple case if you are transferring water from tank from underground tank head to overhead tank. What diameter of pipe should be used? This tutorial is regarding like this. Okay, so transferring any fluid from one point to another, there's two type of friction. Let's start this presentation. This is presentations regarding when I was in EBM as a utility executive. I just giving these presentations to um, my under team, like supervisors, technician, BTech technician, diploma holders, to understand the piping system and operate it efficiently. Okay, this is the complete presentation, but we will cover only short portion regarding the selection of the pipe diameters. Okay, so in the most of the process we have pumps, centrifugal pumps. 80-90% of the pumps in the whole industries for the commercial and domestic, we are utilizing centrifugal pumps, and centrifugal pumps are the dynamic machines that have a main component like itself pump, and its prime mover, which run these pumps impelled by electric motors, diesel engines, or any air system. We can also run this by the gas turbine as well, or compressed air as well. The piping network, which carry the fluid, and the valves and fitting, which have to maintain the flow up to the requirement of the flow and head, and other fitting control instrumentation, etc. Okay, so understanding diameter should be installed by transferring water from one point to another, we have to understand the simple phenomena of static head. What is static head? Is simple vertical height from source to destination. Whether you are utilizing the water from, for this particular example, the water from overhead tank, or transferring water from underground tank to overhead tank. You have the vertical height is static height. It is remain static. Why it is called static? Because the height of the building will not change. So the resistance, the energy which required from transferring one point to another is always the same. The water have to we have to put that much energy to overcome this potential energy. Okay, so this is static head. And the phenomena of water regarding the potential energy or static head is same as per flow. If you increase the flow, the head static head will not increase or reduce. It always the same. Okay, and by simple formula, P is equal to rho GH. Okay, so static head consists of static suction head lifting liquid from related to the pump center line, and static discharge head is vertical distance between the center line. So if you have, like, for example, paint. Okay, let's suppose you have underground tank. In the most of cases, the pump is installed at surface. So this is the suction head, this is water level, this is the suction head. This is the suction head. The water need to suck to the center line of the pump, and this is the discharge head. So overall of static head is like this. This is total static head. Okay. And how we calculate the pressure? If you need to calculate total head by simple formula: density, height, gravity. So this is the height. Multiply this height by density, which is the which liquid you are utilizing. For our case, we are using water, so that density is 1000 and gravity 9.8. So for an example, for a simple case example, if you need to transfer from, like, 100 meter, what pressure should pump produce to drive this water from this point to this point? By simple formula, P is equal to rho GH. Okay, so we have height like 100 meter multiplied by 9.8, gravity multiplied by density of water is 1000. So 9 like 80,000 pascal should produce by the pump. If you convert into the bar, the simple divide by 10 is to power 5, 9.8 bar. So the pump need to produce 9.8 bar to transfer this water to this point, and the pump should produce more than this pressure. Okay, this head is related to only vertical height. The vertical height need to cover to transfer one water from one point to another. Okay, so by transferring water from this point to this one, we have a piping internal flows, and due to the internal flows, we have a friction, and it depends upon the type of a pipe. If you have a very smooth pipe like PVC, you have a low friction, but still you have friction to cover this water to this point. And another thing is fittings, these fittings. Okay, so selecting the diameter of a piping, need to understand the friction due to the these fittings and the friction due to the length of the pipe. So the formula for this we have, you just understand the P is equal to rho gauge formula. You can convert pressure into head or head into pressure. Okay, vice versa. Okay, the behavior, I just explain the static head. The behavior of a water is constant with respect to flow, but like friction, for the friction inside the pipe and the fitting, we have a behavior of water like this. Okay, by increasing the flow, the resistance will increase due to the length of the pipe, due to the different elbows and fitting, so on. So this is the behavior of water. So the total head would be like this. Okay, now you have, for I just give you an example of 100 meter. Now the pump pressure or head should more than 100 meter to overall cover this. This is only the static head. The static head is for this case particular 100 meter plus the dynamic head. Okay, if you draw the picture like this is 100 meter. Okay, so the pump should make pressure like this. It could be 115 depending upon the pressure, depending upon the type of a pipe, smoothness, and also the fittings like elbows and valves and fittings. Okay, the pump should may produce more pressure. This is the dynamic head and it will increase with respect to flow. Okay, so this is behavior of static and the dynamic head. The total head looks like that. Okay, now now the behavior of a pump with respect to flow is like this. For particular example, like this, if you let's take good example like this. Yes, this is the pump. Okay, if you close this valve, this is the gate valve. If you close this valve, the water is not going towards a certain point, but the pump is running. So the pump produce maximum pressure. So like for this curve, if you close the valve, we have zero flow, but the pump make maximum pressure. Now you are allow the water to flow, you open the gate valve, the flow will increase, but the pressure is reduced, and that pressure is going towards the to overcome the friction of the pipe, and then water start to move and move towards the overhead tank. So the phenomenon is like this. You open the 100% of valve, the pressure further reduced, but the flow increased. So it's a irreverse vice versa process. Okay. If you have a maximum flow, the risk of you will getting very high ampere for a motor, so you resist some point. After that, the pump should be closed. Okay, so the behavior is like that. I told you the static head is 100 meter and the dynamic head is like this. So the pump should cover the operating point should like this. Okay, and the pump behavior is like this. If you close the valve, the maximum pressure is like this. If you opening the valve, it will the due to the friction, the pump head reduces at a certain point to meet the pump operating point. Okay, so for the centrifugal pumps, you have a particular requirement like the centrifugal pumps are dynamic machine. They works efficiently at certain values. For example, in this case, you can run this pump at this point too. If you choke the valve, the friction head like this. Okay, so for I just showed you the pump curves. Yes, these are the pump curves line. Okay, so you can run this pump at 40% efficiency and you can also run this pump at 62%. So you have to select the operating values up to the efficiency point of the pump. So you will save lot of energy. Okay, for so also definitely for this system you have to calculate the diameter of a pipe in this way. If you install larger diameter of a pipe, what will happen? The installation cost rises because you don't need to install very large pipe. There's no need. But if you install lesser diameter of pipe, the pump will not flow the water. Pump has some limitation, no? The maximum limitation. For this particular case, let's move towards later, but first conduct this frictional head. The topic we have, like, okay, got it. Okay, after that, you have two phenomena, two behavior of water inside the pipe. We have internal flows. For example, we have internal flows. The water is flowing towards in this in positive x direction. So the water layers are which are near to the skin of the pipe, having a friction. Due to the friction, the velocity is lesser as compared to the center layers of the water. So if the water will run between the between these layers, the water will remains laminar. We called in the fluid mechanics terminology that is laminar flow. Okay, but after certain times, this layer the water puncture up and down and makes the flow turbulent like this. In the start, we have a laminar flow, and after some point, due to the disturbance of the frictions, and it does not depend only upon the friction. It depends upon the diameter, the density, viscosity, and many factors. How we can evaluate whether we have a laminar flow or the turbulent flow? Let's have a very simple example of a candle. If you light up a candle, the initial starting flow is laminar, but after reaching at certain point, you also feel that we have turbulency. So in the internal pipes, the flow is behavior all is more like this. Okay, and how we calculate whether we have a laminar flow or turbulent flow? By simple this formula, dimensionless number, Reynolds number, and the formula is raw VD upon mu. You get this value, you get the value. If you have a Reynolds numbers like this, na, less than 2300, the flow is laminar. The behavior of water with respect to relative roughness of a pipe is linear. Okay, the friction factor behavior is linear with respect to relative pipe roughness. But if you have a flow more than 2300, we have a flakes in the flow like this. So the behavior of roughness with respect to pipe roughness, frictional factor with respect to pipe roughness is for like this. For a smooth pipe, the behavior is like this. For complete turbulence, the behavior is like this. And you have a behavior in between, like in the transition phase. Okay. So for understanding this behavior of water or calculating with respect to accurately, you need to have you understand the flow is laminar or turbulent. Yeah, basic concept of laminar turbulent flow. Right now we don't have just a lot of time to explain all the things, but I have give you basic idea of laminar and turbulent flow. That the flow the terminologies or the equation working behind this is already embedded in this Excel formulas, Excel chart. Okay, you are utilizing Excel chart for calculating the diameter of the pipe. Okay, so move towards our presentation. Okay, so you get the simple idea of laminar and turbulent. Let's have this video. Like if you drop some ink, the layers are maintain its points. It's a laminar flow, but it make turbulency like this. You have a turbulent flow. Okay. Okay. Now move towards our case. For this complex, you will utilizing software like this PyFlow. PyFlow exactly calculate the laminar and turbulent between the section of the pipes and calculating the diameter of the pipes with efficiently. But for the simple case, you can use this Excel predefined charts that is also made by Harlan G. Bengtson. This is PhD professor, and they have a website and these available charts available in the internet. Okay, for the simple case, you can rely on this chart, and these charts are having all the equation related to the laminar and turbulent. You don't need to calculate all the times about the laminar and turbulent. Okay, for this particular case, let's set an example. We have a tank and we have an overhead tank the at the height of 45 feet 7 inch. Okay, this is the vertical dimension. This is the vertical dimension. You have to transfer from liquid from this point to this point. So now what diameter you should follow, and right now we are calculating, and you have optimum flow requirement like flow 1 meter cube per hour, and the pump is producing 3 bar, that is equivalent to the 100 feet. Means if you have zero friction, the pump will lift the water up to the 100 feet of height. Okay, but definitely we have frictions in the pipe, we have elbows and fittings, so it will not lift the water up to 100 feet, but it has maximum capacity of 3 bar, maximum in optimum capacity of 3 bar, and the temperature is 70. So you have to put this data in the Excel chart. You get the diameter, you get the idea of the diameter of the pipe. Okay, now move towards the Excel chart. First of all, you have to assume the pipe diameter. Let's suppose we are selecting 1 inch of pipe, and you have to select the pipe as per standard nominal pipe size available in the market. You cannot put the value as per your requirement, as per your thinking, like point 0.15, 0.10, 2.25. You have to select the type of a pipe that is already available in the market, like size like 1/8, 1/4, 3/8, half, 3/4, 1, 1/4, 1/2, so on. Okay, so let's suppose we select the diameter 3/4 to 3/4, that is 0.75 inch. In the blue mark you have to put the data, in the yellow marks you get the answer by using these formulas. Okay, okay, so you have two type of head loss. One is the head loss due to the piping length, and other one is the head loss uh, due to the pipe fittings like elbows, valves, etc. Like for this particular figure, we have two types of friction. One due to the length of the pipe, okay, and other one are due to the elbow and the T and the valves and so on. So these are two type of friction or head loss we need to encounter. How much margin we have in this particular case is like 100 feet. We can 100 feet, not we have a vertical height 45 feet now, so we have a margin up to the maximum like 50 feet. We can have a head loss around 50 feet, but if you increasing the head loss more than 50 feet, more than 100 feet, the pump will not carry the water. Okay, so right now the pump have capacity to lift 100 feet, but how much static head already given is 45 head. So the dynamic head you have to calculate. This is the dynamic losses. Okay, due to the length of the pipe and due to the fittings. You can go how much you can go, like for this, yes, 100 up to the 50 feet. So you can counter loss around the 50 feet. If not, you can go loss less than 50, but cannot exceed 50 or 55. Okay, so first of all you have to assume the diameter of the pipe, then the pipe roughness. Pipe roughness you can select from this pipe roughness values depending upon the type of the pipe. Let's suppose we are selecting PVC pipe, so its friction roughness is 10 exponent minus 6. So I have just put this over here. The pipe length, how much the pipe length, the vertical height 45 feet 7 inch plus the horizontal section 12 feet 9 inch. Okay, so the total is 58. I put this. The pipe flow rate, we have pipe flow rate in terms of meter cube per hour, so I convert into the CFS, cubic feet per second. Okay, cubic feet. For example, in 1 second 0.01 cubic feet is transferring of water. Okay, this is for a volume flow rate. Then fluid density you have to select the density of the fluid by of this. These are the water. Okay, density and viscosity of water. So at 70 Fahrenheit, density is 1.93 and dynamic viscosity is 2.03 exponent minus 5. I just put over here. So by putting this data, you can have the head loss due to the piping length is around 3.89. This is the frictional head loss due to the length of the pipe. And in the bottom, you have to enter the uh, loss coefficient. Okay, loss coefficient like this due to the length of the pipe we have loss around 4 feet, and for the loss due to the fittings we have to put the values, and the values you can select from this chart: globe valve, gate valve, radius, elbow, T, so on. So let's see in our case how much we have fittings over here. Okay, we have one gate valve over here, one elbow here, one elbow here, two elbow, three elbow, 4 elbow and 5 elbow. We have 590-degree elbow and 2 valves fitting. So just put this value over here like this. We have 5 elbows of short medium radius elbow. Let's select medium radius elbow now, 0.8. 5 multiplied 0.8 plus 0.4. 0.4 why? We have 2 valves. Just simple 2 multiplied by 0.2. We have gate two gate valve na? Fully open. Let's suppose we have fully open gate valve. So we have friction loss due to the fittings is 4.4. The total loss is 8.29. So total means total head is equal to 45 feet plus 8.29. Okay, still the pump capacity is 100 feet, so you will get this minus this. Okay, still the pump is running, the pressure coming over the pump is 46.71, means the pump will run like this. Okay, if you go in the presentation, yes, so you have a total static head plus dynamic head is like 47 huh? The pump will shift like this. Okay, let's have a presentation. Okay, yes. Okay, so your static head is 45. The dynamic head total by selecting the 0.34 diameter of. Okay, so you have like 48, I think. No, 48 means 8 minutes. How much loss? 8.29. So it is 53, na? 53, 45.829. Yes. We have total static plus dynamic head is 53. The pump has maximum, with respect to flow, na, the pump, this is the optimum value, this is the optimum value. Okay, this is optimum value 1 meter cube per hour, and flow is around 100. Okay, sorry, this is more than that. So you have to shift pump towards this point. So you can, from this, the pump is running basically at this point. Okay, at this point. So from this you can understand, you can reduce the diameter of pipe by installing 3 upon 4. You are putting extra installation cost. You can reduce the diameter because still you have a margin. You have a lot of margin, na? 46, you have 46. You can reduce further loss up to the 46, maximum to the 46, because you have some factor of safety, like you cannot put 46, you can make 40 or 35, so on. So further reduce the size. Let's take diameter of 0.5 inch. Now how much total friction loss is 31. So 31. Okay, now so you have margin of 24 feet head loss. It is adjustable. If you further reduce, like 3 8, 3 divided by 8. Oh, then you have a friction loss is around triple one. You will get in the negative. Like the pump will not run. Okay, the pump will not. If you select 3 8, the flow will restrict. The water will restrict up to this point 56. It will not further move toward this. Okay, so the optimum diameter from this way you can select the diameter. The optimum diameter is 0.5. So from this value you have to, and you are able to calculate the diameter of a pipe. Which diameter should you should select by transferring water from one point to another. Okay, so this is let's make it short. In the later video, I will further explain the phenomena of the pumping, the piping systems, further its detail of laminar and turbulent, and these formulas that working behind this phenomena, like these formulas and the ducting. We will discuss it later. But right now, you have a short tutorial for utilizing this Excel chart. Take this chart, uh, draw these kind of drawings, and submit your OEM. Thank you.